Hello everyone. Today, I Chirag Katkoria from ICT Section B is going to explain you about our project, which is based on the determination and prediction of the behavior of tumor growth in our body. It is quite interesting to know that how calculus helped us in modeling the tumor growth. We as a team have reviewed lots of literature available pertaining to this domain to understand about this. Our main goal of our project is to determine the growth of the tumor cells using mathematical models. But a question arises, why only tumor? Why only cancer? Because cancer has become a significant cause of death globally. It is the second leading cause of death all over the world, according to the report of World Health Organization in 2018. And so it becomes necessary to research about it. After a certain level, the cancer also starts spreading all over the body through a process which is known as metastasis. It starts spreading through other organs, which is evident of how deadly the cancer can become. So basically, the most used models are the deterministic model and the stochastic model. There are two types of models. The Now we will discuss about the mathematics of all these models in brief in this presentation, which I'm going to do now. And so first of all, we will talk about the deterministic models, because deterministic models rely specifically on differential equations to model the tumor growth. They aim to mathematically express the tumor growth and predict the future rate of the growth. They simplify some complex factors which may introduce variability in the growth of the tumor. So they are generally based on the exponential models. There are seven types of different deterministic models, and the first of all is the exponential model, which is probably the most simplest model to determine one of the most complex diseases in the world. So according to the exponential model, the tumor cell divides into daughter cells exponentially. And this is the equation ln Vt is equal to Bt plus ln C, where B is the kinetic parameter or a growth rate constant. And we can also find the doubling time of the volume of the tumor cell by putting V is equal to 2V0, where V0 is the initial volume of the tumor growth. This is also known as the doubling time, which comes out to be ln2 divided by b. Now, we obviously know that exponential model failed to predict the cancer growth because it it was found that it follows the initial stages of the growth of the cancer, but it fails to explain the later stages. Now we come to the Mendelssohn model, which is not so much different from the exponential model, and the growth rate is shown to be proportional to any power c of this population. The equation of the model is dv by dt is equal to b into v to the power c. So now it also failed to predict the growth properly. So now we will talk about the linear model. According to this model, the growth of the tumor becomes linear after a certain threshold time or certain threshold weight. First, in the initial stages of the tumor growth, it follows an exponential model, and after certain time, it switches to the linear growth, and it becomes constant with time with the equation V is equal to V naught plus R into T. This model also not completely passed to determine the tumor growth. So now we will talk about the logistic model, which is a good model to predict the tumor growth, because according to the previous models which we saw, the growth occurs indefinitely, and so there is no limit, which is impractical. Any tumor cannot grow till infinite time. So now if we see the logistic equation, we can easily find out that there is an extra parameter known as k, which is the carrying capacity or the maximum growth of the volume of the tumor. As the tumor grows, the rate of the growth decreases as it approaches a maximum size k, and when v becomes equal to k, the dv by dt becomes 0. So if we realize that this is a slight better model than the previous models we saw if compared to others. So there was again a model which was proposed by some scientists, and this is known as the surface model. It arrived and it mentioned that the parent cell divides into daughter cell, which is known as the process of mitosis. only on outer part and inner cells are mitotically inactive, which is not so much practical and not logical. So now we will talk about one of the most famous and used growth equation, the Gompertz model, which is best fitted into the clinical data, and most scientists and researchers use this model to model the tumor growth. And it becomes very necessary to understand about the Gompertz model in order to understand the cancer growth. Gompertz model wins the race among all the models as it best fits the growth of the breast cancer. And if we talk about it, it is famous for its simplicity and accuracy. Gompertz model has also the ability to show the later stages of the tumor growth, which the previous model failed to do so. After some inflection point, the tumor growth starts decreasing. The rate of the tumor growth decreases exponentially according to the Gompertz model. And so it is the graph of the Gompertz model is an S-shaped sigmoidal curve which has also an inflection point which is asymmetric. There are two asymptotes as well. So now after doing some mathematics and after assuming something such as that the shape of the tumor is a sphere and tumor is a solid mass made up of the tumor cells. After taking these two assumptions, we integrate the equation and we got the final equation as V is equal to beta into e to the power minus c into e to the power minus alpha t, where alpha, beta and c all are greater than 0. Beta represents the maximum tumor volume at the infinite time. So when the t tends to infinity, then the maximum volume the tumor cell can attain is beta. And the maximum carrying capacity, let's say it's k, then this behavior is known as the asymptotic behavior as well. C is the displacement of the time along the horizontal axis, and the parameter alpha is the volumetric growth rate or the constant growth rate. The point at which the growth rate gets its max volume is known as the inflection point. And we now want to show you a sigmoidal curve and how it looks like. It's like almost an S-shaped curve with an inflection point as well, which has an inflection point. And if as the volume of the tumor increases, so the term C into e to the power minus alpha t will also increase, and so the tumors per volume, the rate will decrease. Gompertz equation is also good as it has a good predictive ability to determine both types of the growth, unhindered tumor growth as well as the hindered tumor growth. So from so many observations, we will try to find out the constants alpha, beta and c of the Gompertz equation, and we can find out the constants based on different situations. And if we plot the graph based on this constant of the Gompertz equation, we found a curve which almost matches the curve of the clinical and experimental data of the breast cancer. This is the curve. We can see that the orange line is the Gompertz curve and the blue line is the clinical data. It almost matches. So if the parameters are chosen specifically, the model can become successful. So for the particular graph we saw before, these were the values of beta, C and alpha. Still, this model was very successful, but there are some few limitations as well for the Gompertz growth because it tries to simplify all the complexities and complex nature of the tumor dynamics, and it does not take into account many uncontrolled factors. This model is not suitable for all kinds of tumor because it ignores the intercellular interactions between the cell and the immune system. So it is not a complete model to determine the tumor growth. Certain few noteworthy research articles we saw while reviewing the literature also mentioned that the goal of any mathematical modeling should be to understand the real mechanism of the system fundamentally and should not just predict the future growth rate. So this is where Bartel-Henry model also comes into picture as it is biologically motivated, which is not the case with the Gompertz model. Gompertz model is not biologically motivated. Von Bartel-Henry introduced this model trying to show a balance between synthesis and the destruction of the cells. It also says that the volume of the tumor increases to the surface area because the nutrients enter any spherical cell, if we consider the tumor as a sphere, through the outer surface. So before giving the Bertalanffy equation, a simple ideal condensed differential equation, also known as the Bertalanffy-Putter differential equation, is given here, which is dv by dt is equal to a into v to the power p minus b into v to the power q, in which the dimensions are already given, and it is also known as a generalized equation because if we put different values of the exponents and constants, we can even get exponential model and logistics model. Bertalanffy chose p as exponent is equal to 2 by 3 because he believed that the inflow of the energy is proportional to the surface area, and so in order to adjust the dimensions to convert the volume into area, he chose the exponent of 2 by 3, and the exponent q is equal to 1 because the energy sustenance is directly proportional to the cell count. And so by choosing v is equal to k cube, the equation of the Bertalanffy model can be determined, and this is the equation of the Bertalanffy model, where if we make the derivative of v with respect to t as 0, then we will find that v is equal to a by b cube is the saturation level where dv by dt becomes 0. And thus, if we try to plot the graph of this, if the initial volume is less than the saturation level, then it will increase exponentially till the saturation level and then it will become constant. If the initial volume is greater than a by b whole cube, then it will decrease exponentially to reach the saturation level. And so this is the graph of the Bertalanffy model. But still there are many drawbacks of the Bertalanffy model because the detailed biological processes cannot be explained by just comparing them to data. It becomes very difficult to compare such a macroscopic data and explain each and every underlying biological processes. For example, the formation of new blood and lymphatic vessels, which is known as the angiogenesis. So now we will talk about our next session, which is the stochastic mathematical model. Stochastic model takes into account unpredictability while determining the tumor growth. The variability is also introduced in many deterministic models also in order to introduce the stochasticity, because tumor growth does not follow a fixed differential equation. Instead, it is a very complex process and therefore it needs some unpredictability and uncontrolled factors to determine it. So in simple terms, there is a Markov chain, and in order to describe this model, we can understand Markov chain, which is a stochastic model describing a series of events in which the occurrence of an event depends on the state attained in the previous event. We can easily determine that stochastic models are way more complicated than deterministic models, but they are also more realistic. So in this section, we will talk about two types of models which we already discussed in the deterministic models, Gompertz model and the logistic models, and they will be extended to their stochastic counterpart. So in the stochastic Gompertz model, the Gompertz model was not able to take into account the unpredictability and the uncontrolled factors, and so it was extended to their stochastic counterpart. And the data of this model with the clinical data seems to match for breast cancer and cervical cancer. Here we have stochastic differential equation in which a stochastic component is added to the equation, which is sigma into v into dwt, where sigma is a diffusion coefficient. It is always greater than 0. It represents the intensity of the stochastic part. Larger value of the sigma means that there is a large fluctuation or large unpredictability variability induced into the equation. Here dWt represents the Brownian motion or the Wiener's process, which represents the change in the Brownian motion. So let's try to understand about this stochastic processes. Brownian motion is discovered by a British botanist, Robert Brown, and oftenly Brownian motion and Wiener's process are used interchangeably. So let's try to understand this complex process by a simple example of walking. While walking, we start in any random direction. There is no predictable pattern of our walking. By taking these random steps, our path becomes continuous, though it is jagged, but it is continuous because there is no break or jump. We cannot predict our steps, and each step is also independent from our previous step. So Vinea process is just like that. It is random but a continuous movement, and independent increments as well as erratic nature are also one of the key features of this process. So let's talk about the stochastic logistic model. Just like the Gompertz curve, it is the extension of logistic model to the stochastic counterpart. So now these are the equation in which the stochastic counterpart is added to the original logistic equation. We will talk about some another mathematical models as well, and one of them is the pharmacodynamic model. This model is almost similar to the exponential linear model because at first the tumor growth follows the exponential model and subsequently the tumor follows the linear model. So let's talk at some threshold tumor weight, let's call it WTH, when the tumor growth switches from the exponential growth to the linear growth. And so in terms of calculus, we have also set different two equations which will be combined later on. When the tumor mass is less than the threshold tumor weight, then the dw by dt will be equal to lambda naught into wt, means it will follow the exponential growth. And when the tumor mass becomes greater than the threshold tumor weight, then it will follow the linear model. Here lambda naught and lambda 1 are the parameters for the exponential growth and the linear growth respectively. Both the parameters also have a relation. Parameter of the exponential growth lambda naught is equal to the threshold tumor weight times the parameter of the linear growth lambda 1. Above two equation can also be used as a single function, and in this single function, when tumor mass is less than the tumor threshold mass, the term in the denominator is negligible if compared to 1, and hence the growth becomes exponential. And when the tumor mass is greater than the tumor threshold mass, 1 becomes negligible, and therefore after 2 or 3 steps of mathematical calculation, we can find that the tumor follow the linear model. And so now we would like to conclude our project, our findings and our literature review. We chose cancer as one of the most important topics because cancer is one of the most deadliest diseases in the world. It becomes very necessary to determine its growth, to find and proper accurate treatment procedure to solve the problem of the cancer among many patients. So we have also tried to summarize the two most used and research models, the deterministic model and the stochastic model. Also among the deterministic model, we found that the logistic model as well as the Gompertz model were successful in predicting the tumor growth. And to account for some uncontrolled environmental external factors, they were also extended to the stochastic counterpart because they were not accounting any uncontrolled factors in the deterministic model as it follows normal differential equation, but in the stochastic model they follow stochastic differential equation, which is also known as the SDE. The stochastic Gompertz model seemed to best fit the clinical data as we have seen earlier, and so in this way there are lots of models proposed by different scientists and researchers as well as mathematicians for the tumor growth, and the research is still going on. There is a huge potential of research in this field. And these are the references for our literature review which is done by our team in the project. Thank you all.